I saw this film once, old, black and white. It was about a scientist who invented a new fibre that was going to revolutionise the textile industry. The thing is, it was white, but it never got dirty, never stained, never wore out. And yet nobody wanted it, not even the rag and bone men, the recyclers of the day. They needn't have worried. The suit dissolved in the rain, and recycling went on to become one of the biggest industries in the world. Do you know that every year in Britain alone, 5,000 million cans like this are recycled every year? You know why? Because it's aluminium. What do we know about aluminium anyway? Well, it has a nice, simple atomic structure. It's a metal with fairly small atoms quite a long way apart. That means it has a low density. It feels light. Its properties make it an almost ideal material for recycling. It has a fairly low melting point, and it doesn't corrode much. So, John, you're a smelter, an aluminium smelter, is that right?
Yeah.
Which means you take scrap from all over the place.
Yeah.
And you've got sort of Coke cans and bottle tops and printing plates and goodness knows what.
Yeah, from all the aluminium, different types of aluminium scrap, we grade it, melt it, and make a finished product.
All you've done is put scrap aluminium in there, is that right?
Yeah, that's correct, yeah.
Can I add my bit?
Yeah, no problem.
Okay, great. Right in the middle. Terrific. So, all you're doing is taking scrap, melting it, and getting nice pure stuff out the end.
Yeah, that's correct, yeah.
Now, your furnace, what's it powered by?
Reclaimed oil.
So that's relatively cheap. It's already been used once.
Yeah, it's relatively cheap, and it gets rid of all the messy oil.
Right. What sort of temperature are you running at?
900 degrees.
It does certainly feels quite warm even from here, doesn't it?
Yeah.
You just have the flame belting out into the air above the metal.
Yeah, it doesn't actually direct it onto the metal because it would make more dross. It's just above the metal.
Okay.
And it's just the heat it's getting, not the actual flame.
So you're trying to prevent oxidation, basically?
Yeah, that's right, yeah.
Okay. And what about all the paint and old, sliders and things in there?
Well, that just burns off and turns into dross and floats on the top.
Okay. And what's in the dross? Is it oxide?
Yeah, it's some oxide, but it's still about 30% aluminium.
So this is where it's coming out, yes?
Yeah, we're pouring at the moment. That's the molten aluminium coming out of the furnace.
What sort of temperature is that?
About 850 degrees.
So it's quite warm?
Yeah.
The melting point of aluminium is 660, is that right?
Yeah, upwards because of the different alloys, yeah.
Oh, I see, okay. And these are just going to be ingots?
Yeah, aluminium ingots, yeah. They go up the conveyor and they cool as they're going up and drop off the other end.
What, in 3 minutes or something?
Yeah, they water cooled as they get near the top and then...
Terrific, so it doesn't take long?
No.
I've got this lump of bauxite here, this is the ore, isn't it?
Yes.
This is the stuff they extract aluminium from. Now, if we put this in the furnace, is it going to melt?
I don't think so, no.
Can we try it?
Certainly.
Okay, you've got a ladle there. I think I'll be brave and let you do this.
Right, okay.
Off you go. For about 10-15 minutes.
Yeah, that's right.
And this is what? 500 or 600 or 7, maybe more. But the bauxite hasn't changed at all.
No.
It's still solid, hasn't melted.
That's
so
right.
it's going to take a lot more energy than that to get the aluminium out of it.
Yeah, that's right.
So you've got a fantastically simple process here, just a little bit of waste oil, and you can turn scrap aluminium into fresh aluminium.
Yes.
Whereas obviously to turn bauxite into aluminium requires, enormous amount of electricity.
Yeah, that's correct.
It's really good news, that.
Yeah.
Well, I think I'll keep well out of the heat, if you don't mind.
Okay.
It takes 15,000 kilowatt hours to make just 1 ton of aluminium. Currents of thousands of amps are used to electrolyze the aluminium oxide and keep it molten at temperatures approaching 1,000 degrees Celsius. In the pot room, the electricity is splitting up the aluminium oxide, purified bauxite, into aluminium and oxygen. This oxide is very stable and needs enormous amounts of electricity to do this. The high current keeps the electrolyte hot so that the aluminium produced is a liquid. Impurities are skimmed off the surface of the new metal.
So it's the difference between melting and electrolytic reduction. The saving in cost is the saving in energy. Aluminium's a metal with fairly large atoms quite a long way apart, so it has low density. That means that extracting it from its ore is enormously expensive, but recycling it by melting can be done relatively cheaply. Sounds promising for the granddaddy of all recycled materials. I know what that sounds like. Any old iron, any old iron, any old iron. You look treat and you're walking down the street. Old iron, old iron. Now, just like aluminium, iron has a close tapped atomic structure, but the atoms are a bit smaller and a bit closer together, and that means that the forces that hold them together are stronger. The result of that is that iron has a much higher melting point than aluminium. Nigel, this is your raw material, right?
Yes, it is indeed.
It's covered in rust.
It doesn't matter.
Why not?
Doesn't matter. Just when you stick it in the furnace, it just floats off onto the top, makes a slag, skim it off, throw it away.
You can just scoop it off?
Just scoop it off, you know.
This is scrap iron, yes?
Yes.
And what proportion of iron is there in it?
It's roughly 95% iron.
Oh, so there is a lot of iron, despite all that rust.
Yes.
Now, I've always been confused. Tell me the difference between iron and steel.
Cast iron, basically, is about 3%, 3 to 3.5% carbon. Steel is 10 times less. It's about 0.3% carbon.
10 times less.
10 times less carbon.
So steel is almost pure iron.
It is, yeah.
And iron has got a load of carbon in it.
It has indeed.
That's
yeah.
quite complicated, isn't it?
Very.
Good. So, all right, we now know the difference between iron and steel.
Yep.
Can we go and see what you do in the furnace?
We certainly can.
Let's go and have a look. What about the temperature of the furnace?
We tap it out, the metal out, at 1,500 degrees.
1500.
We use an induction furnace.
You put a huge current through your coil around the outside,
Yes.
and that induces a magnetic field inside your lumps of scrap, and that changes backwards and forwards.
That's right.
And they get a bit warm,
They get hot.
1500 degrees.
Yes.
So you must use quite a bit of electricity.
We use 600 kilowatts, which is just over half a megawatt.
So a microwave uses about 600 watts. So you're using 1,000 times. It's like 1,000 microwaves in that.
It is, yeah.
I can imagine it gets quite hot then. Yeah. So you're just pouring it into this bucket,
We're
yes?
pouring it into this bucket now. This is the ladle. A certain amount of magnesium in there as well, which will flare off and make that white smoke, which is magnesium oxide.
Oh, yes.
And this is for making ductile iron.
And what's this for?
What this does, it turns the graphite in the cast iron. It's normally like cornflakes. It's like in little plates.
Right.
So when you put the magnesium in, it turns it into little round balls. And that's what makes the iron ductile.
So when you say ductile, it'll
It
pull
stretches before it snaps.
and it'll bend.
It'll then, you can forge
Right.
it, you can do all those things that you can normally do to steel.
So the process is terribly simple. You simply sling the scrap iron in. You've already taken the slag off, yes?
Yes,
And now you melt it and pour it out.
that's it exactly.
And then you have to pour it into these
And we
molds.
pour it into these molds here behind us.
Wonderful, isn't it? Just white. I mean, it could be water, except that it's a bit warm.
Yeah, it amazes me how runny it is. I mean, considering it's iron,
Yes.
you'd have thought it would have come out like treacle.
Sticky, but
But
it's
it's runny as water.
very, very mobile, isn't it? Yes, lovely.
It's absolutely incredible. It amazes me every time. I mean, I've been watching it for years and I'm still amazed by it, even now.
Right, terrific. So, Nigel, these are your products.
Yes, they are.
This looks to me like steel.
It's cast iron.
This is cast iron?
It's definitely cast iron.
Right. Why don't you make such a thing out of steel?
Well, the snag with steel is it buckles when it gets very hot. And before you know what's happened, the whole thing's twisted and it's starting to come away from the block. One of the properties of cast iron is that it'll just get hot, it'll grow a little bit because it's got hot, and then it just goes back, but it just sits there nice and stable.
So that's what the carbon is doing for you in the lattice, right?
Yes.
It's preventing it from buckling, from changing shape.
Yes.
So it's I mean, iron is better than steel.
Iron is a different material from steel.
I always assumed, you know, that rusty old things were iron and that smooth, shiny things were steel.
Which is absolutely not true at all.
Right.
There's plenty of rusty steel.
Simple, isn't it? Melting's always cheaper than reducing an ore because it uses less energy. And almost any kind of scrap is likely to contain a higher proportion of metal than any ore. But some materials do deteriorate with use. This is paper. I'm told that if you recycle it more than 7 times, the fibres simply fall apart. Hi, Paul. So what's this?
This is a hydropulper.
Right.
What we've got here is bales of waste paper, water,
Oh, yeah.
being slushed up using a high-speed rotor at the bottom.
Right, so your basic raw material is this, used cardboard.
That's right,
Are you telling me that you can turn this into something just as good?
more or less.
Really? I'd be very interested to see how. Paul, what's this stuff?
This is starch.
And what do you put that in for?
Put that in to increase the strength of the paper.
The strength.
Yes,
Is that because the fibres get damaged in the recycling?
yes,
So they're not as strong as new fibres?
that's correct.
And this brings it back up again, does
Yeah, more or less.
it? Okay. Where does it come from, the starch?
It's corn starch.
Corn?
Yeah.
So it's not old potato peelings?
No, that's right. They make us eat corn on the cob.
Do they?
Chuck the husk in.
So it's no good my eating fish and chips, it's no use at all?
No.
Okay. Oh, it's incredibly hot and humid in here. It reminds me of the Indian monsoon. I can't see a thing. Ah. You've already added the starch.
That's right.
What else do you add?
Well, apart from on this particular grade, it's just starch. But on other grades, we do add a bit of dye.
Bit of dye.
Yeah.
So this is just that sludge of old cardboard mixed with water and a bit of starch. How much water is there in there now?
It's over 99% water.
99% water. Okay. And what happens at the other end of the line?
It's been dried down to 7% by the time it gets down to the other
Dry
end.
down to 7%.
Yeah.
In how long? It's about 50 yards, is it?
Yeah, probably 15 seconds.
15
Yeah.
seconds. So you're getting 90% of the water out in 15 seconds.
That's right.
That's why it's so wet up here.
Yeah.
So it's just going backwards and forwards around heated rollers, yes?
Yeah.
Now this is your end product.
That's right.
Is that this layer of paper?
No, it's the fluted bit in the middle.
The corrugations you're making?
That's right, yeah.
And is this as good as the original?
More or less. It's a little bit dirtier and it's still not quite as strong.
Not quite as strong, so
No.
you can tear bits off it.
Yeah.
Right. And the dirt, what's that?
That comes mainly from printer's ink. and things like
Printer's
that.
ink.
Yeah.
Right. Now there is a way of getting rid of that. Let me show you how. In this jug, I've got some recycled newspaper pulp, and you can see it's quite mucky with a little bit of soap in there. And coming through this blue tube, I've got some compressed air, which is blowing out the tube at the bottom of that. So if I slop this in here, and I'll try and get most of it inside. Oh yes, quite a lot's going in. What I'm hoping will happen is that as the compressed air bubbles up through this solution, we'll get froth forming, and the ink from the newspaper printing will stick mainly to the bubbles, and so they'll float up to the surface. This is called froth flotation. Well, it certainly seems to work. The dirt certainly seems to be sticking to the bubbles up here, and clearly you could just scoot them off the top, and then you could have nice clean pulp at the bottom. And I'll show you somewhere else where a very similar process is going on. This is water that's been used in the plant, and they want to use it again, but the trouble is it's full of fibres. So what they do is another bit of froth flotation. They actually put it in this tank and they blow compressed air up, and the froth made by the compressed air floats the fibres up to the surface, and here they all are in great clumps on the surface, And this machine comes along and scoops them up, leaving clean water underneath. At least paper is biodegradable, so if the worst comes to the worst, you can bury it, or you can burn it and get some energy out without causing too much pollution. But this stuff is a nightmare. Plastic, huge long chains of atoms with very, very strong bonds between them. And there's an additional problem here that loads of different kinds of plastic are often mixed together. In this yard, you begin to see the size of the problem. It's full of bottles, different sizes, different shapes, different colours. They're made of different materials, they've got different caps on them, and they're full of liquids. The real trouble about having different sorts of plastics is they behave differently when they're heated. Now, these things, floppy disk covers, are made of polystyrene, which are basically those long, long chains of atoms all tied together, but just chains lying side by side. Whereas this clutch plate is made of a thermoset plastic, so when you heat it up, it won't melt, it'll just burn. Let me show you what I mean. I've got a blowtorch here, and there we go. If you look at this clutch plate here, I'll hold it up so you can see. It's charring, it smells horrible, but it's showing no signs of melting. It's not softening, it's not changing shape, it's only charring, and that's because those long, long molecules are cross-linked. There are bonds between the long chains. They can't slide past one another. The only thing they can do is burn away from the surface. So what are your most successful products at the moment?
The bollards and the picnic tables are the most successful ones we have running.
The bollards.
Yes.
So what are these replacing?
These replace the cast iron bollards you see at the side of the road in the city centres.
Oh yeah,
And these are the traffic bollards are generally concrete.
concrete.
So we make these products so the concrete ones break very easily when you're touched by a car.
Right.
And so these don't do.
So these
These
bend,
can bend slightly and come back into position.
come back and knock your teeth out. Something like that. And these are made from old milk bottles?
They're all milk bottles and back of store waste, which is polyethylene packaging waste. Which is
Okay.
your polythene bags, basically.
So obviously that's very good news, isn't it?
It is, yeah.
And now this is obviously just a chunk of wood, isn't it?
It is. It's our new product called knotwood.
Not wood.
Yes, because it's called knotwood because it's not wood. It's a mixture
That
of
is a terrible joke, if I may say so. So what is it?
a combination of waste wood and plastic mixed together with some chemistry in the middle to join them all together. So we're utilising waste wood and plastic to make a new product which is superior to the plastic products we make today, and it's replacing the wood.
So is this the future?
It is.
Terrific. In fact, there's a general problem with the science of recycling. Everything's mixed up together. Metals, paper, glass, plastic, ceramic, and old cat food. You name it, they have to sort it out. And some of these things are much easier to disentangle than others.